Okay, folks, this is David Collum speaking to you about experimental synthetic organic chemistry. This is a lecture that I've given at Cornell many times, even exported it to a couple industrial groups over the years. It's evolved over the last 40 years. There are three target audiences for this particular recording. Number one is our two chemistry courses. One is Chem 301, the laboratory course, which is now on virtual learning because of the COVID virus. It's April 10th, 2020 that I'm recording this. Number two is Chem 666, which you can see in the upper left corner, which is a graduate course, which I normally view as my primary target audience when I give this lecture every year, usually on a Friday night. It takes about 3 hours. And then finally, I'm going to upload these recordings to my website. Affiliated with this recording is a Word document that'll be uploaded there too, and uploaded to Canvas for the two courses. That'll have hot links and stuff, and you'll see them as they go. Occasionally, I'll make reference to Chem 301 students because that's the primary target for this one. And let me tell you a little bit about the background. So I haven't done synthetic chemistry in probably 38 years, but I still consult and I still read the literature on it, and I'm pseudo-marginally up to date on the subject. The origin of it is that when I was in grad school, I worked with Clark Still, who was not only the best synthetic organic chemist in the laboratory and possibly by design that I've ever met, but he was truly almost unimaginably good in the laboratory. And so I've drawn here a picture of a molecule, monensin, which we made along with Clark and I and John McDonald, who ended up running MedChem at Lilly. And we made it in my second year of grad school. Now, I got to tell a background story here. It's funnier than hell, actually. Clark sat John and I down at the end of our first year of grad school. As I recall, it was June 5th, 1978. And he drew this molecule across the board. And even by modern standards, it's a pretty serious chunk of molecule. But by 1978 standards, it was enormous. And just to calibrate you, we had 80 megahertz FTNMR, and that was it. I didn't record a single C13 spectrum in grad school. And we had mass spec that was marginally useful, run by a guy who was, in my opinion, marginally crazy. No crystallography, no prep HPLC. We used some medium pressure liquid chromatography and analytical HPLC. And Clark drew this molecule across the board, June 5th, and he turns to John and I and he says, we're going to make this molecule, and we're going to make it by August. And he was talking about August 1978. And so John and I thought, well, this is going to be exciting working for a crazy man. And what I'll tell you is we, at one point, looked like we were going to hit that target. And we ran into some snags, and we made it over the next 14 months. It's what got me a job. It's what got me, started. And if you put me in grad school 100 times again, I would not be able to replicate what happened during that 14-month period. So for me, it was sort of like Miracle on Ice was to hockey. And we all worked really hard. Clark's design was truly stupendous. And but more importantly, a lot of the methods and philosophies that he somehow cobbled together and taught us allowed this to happen. And so that's why I give this talk. Some of it may look a little dated to people who are much more automated, but I think the philosophies still hold true. And so here we go. And just check and make sure we're still recording. So let me talk about philosophy. When we first joined the group, Clark said you should be able to do at least 2 reactions a day. Now, in the age of parallel synthesis, 2 reactions a day seems trivial. We used to do up to 10 a day. We did a lot of things in substantial parallel. I'd run 20 or 30 TLC scale reactions a day, easily, just to make sure things look good by TLC before I committed serious material. It's not a coincidence that we're running in parallel, and it's not a coincidence that not too many years later, Clark started one of the first combinatorial companies and made himself many millions of dollars doing so. What he told us is basically we should make progress daily and really nail the solutions in the very least weekly. And one of the things he conveyed is that it doesn't take long to rule out all the possibilities and change plans. So let's talk a little bit about free time. There's some hypocrisy in this part of the lecture. If you have free time, there was a point where I don't think I had a desk in the lab. I used to keep my notebook at the bench, and I'd sit on a stool. First cardinal rule is if you have free time, set up another reaction. If you keep doing that, you will not have free time soon enough, and it will solve your problem. I used to consider a day was a good start if I could finish 2 reactions by noon. If you have free time, you should clean glassware. I used to keep a list of things, menial chores to do in case I needed a brain jarring, but your sink should never be filled with glassware. You should always be cleaning as you go. As one of my former colleagues said, if you have time to lean, you have time to clean. And so the people who commit an hour at the end of each day to clean up all their messes are wasting the 5-minute slugs. So you should complete all miscellaneous and menial chores during these little windows. Do things while a TLC is running up the plate. You should read. I kept copies of things to read at all times at my bench, so while the TLC ran up the plate, I would read Feeser and Feeser or something, or some book or whatever, and work my way through. I worked my way through all the chapters of Feeser and Feeser, doing TLCs basically. Again, grad students, I encourage you to read at least an hour a day. It's hard. It sounds easy. It's not. You got to be diligent. And then the modern variant is, stay off the internet. Now, I love the internet, so that's where the hypocrisy comes in. But I can guarantee you if I had a laptop or an iPad and access to the internet in grad school, I would not have been as successful. That's a guarantee. Somehow you have to get control of that. And I'm 65 years old. I can get away with murder. Most of you guys listening to this are in your teens or 20s. You've somehow got to find a way to push yourself away from your computer. And it's increasingly difficult as, experimental chemistry, you do interfaces with the computer so much, but somehow you got to do it. And I don't know what to say besides the fact that the kid who is able to achieve that is the kid who will excel. And one of the beauties of organic chemistry is you eat what you kill. It's not hard to be a great synthetic chemist, in my opinion. It's not hard to be a great organic chemist. It's grit. It's MacGyver. It's the P chemists need brains. They need to be able to do math. We don't. Caution versus speed. Synthetic chemists are slop jockeys. So I think it's a lot more like hockey than being a sniper. And so shots on goal are important. Cut corners when appropriate. And I'll show you all sorts of ways to cut corners. And, there's people who can spend the better part of an afternoon doing something that I would say skip it. And so at the same time, you have to know what corners you've cut, because once in a while a reaction's tricky. And if you're just a pig, you'll never figure out what it is you're blowing. So cut corners when you can. If you cut one and it was too sharp a corner, you set it up again. Don't forget, if you have free time, set up a reaction. So you have to slow down when necessary. Every once in a while you hit one. I had a couple in grad school that only in retrospect did I understand how I was blowing it, and I just didn't understand it at the time. So planning an experiment, again, this goes all the way back to when I was a grad student. Multiple parallel reactions. Those people who insist on setting up one reaction and babying it will move very, very slowly. I've only had one grad student who was an exception to that rule. He ended up being a VP advisor. He was very good. And But he's a sharpshooter. But for the most part, I think you want to run a lot of parallel reactions. If you have to hydrolyze a protecting group and you're not sure of the conditions, you might as well run 15 or 20 at a time. You can spend a lot of money on fancy equipment to do this, or you can set up a bunch of fused pipettes or something and run 50 microgram scale TLC reactions and just run them all in parallel, run them all up the same plate, and we'll talk about that. And you also have to learn how to juggle unrelated reactions. It's not just parallel for the same reaction looking at different reagents. I mean, if you can run in parallel, say you have to do an oxidation, if you can run in parallel, you can test every oxidizing agent known to man in a day. I remember watching Clark one day facing a difficult problem with an aldol condensation, and he's getting funny results, and he did 12 of them that day, and at the end of the day he understood what the problem was. So he spent a total of 10 to 12 hours solving what was a major problem. Okay. There. How about scale? Well, I am going to try to beat into your skulls that the smaller the scale, the faster you will move. And there's people who feel very comfortable having vast quantities of material. That's a phobia. You have to get rid of that. First of all, never go into biochem because you never get big scales of anything. But lower scale, smaller, faster rates that you'll move. And so what are the scales I worked on? TLC, 50 to 100 micrograms. So if you have a small amount of material you're working on the front of a synthesis, you can do an awful lot of TLC scale reactions. And again, TLC to me, despite all the technological improvements, TLC is still the absolute core of any bench chemist. And I was at Jotham Coe's retirement dinner at Pfizer, and he gave a talk, and he emphasized, he says, don't forget TLC. With all those automated HPLCs, he said, don't forget TLC. Small preparative for us was 0.5 milligrams, which you can take several steps if you don't have the phobia. Up to 10 milligrams. I'd call that small preparative scale. Your goal as a synthetic chemist is always, first and foremost, your very first goal is to get a tiny quantity of the desired material. You want to find it, you want to characterize it, at least to a limited extent. And after that, you can worry about how to get more of it. And so in any event, small preparative, 0.5 to 10 milligrams. Preparative, 10 milligrams to a gram. A gram is huge. A gram's the top end of preparative for me. And then macro scale is anything over a gram. And you can do total syntheses on these kind of preps. Usually the first couple steps are multi-gram, but once your ways in, you should be working on very, very small quantities. So how about scale up? Well, scale up's dangerous. The scale up blues, they can really hurt you. I blew a few of those myself. Surface volume issues change. When you scale up, bear in mind that you don't want to change the conditions unnecessarily. So I would have to say, as a grad student, I didn't appreciate the importance of getting the concentrations to stay the same. So I would say, well, who cares if it's dilute? Well, as a kineticist now, I realize that if you have a reaction that's third order in all your reagents and you cut the concentration in half, you just increase the time of the reaction by a factor of 8. So pay attention to concentrations. When you scale up, do a 3 to 5 fold. You really don't want to create messes. Avoid large-scale preps, even lit preps on a first attempt. The bigger the prep, the bigger the mess. And so if you haven't done a reaction for the first time, if you're doing a reaction for the first time, you should do it on a quantity be willing to dump into the waste bottle. You want to be able to punt the ball when you can. And if you do it on too big a scale because you cross your fingers or even if it's a lit prep, if you get a kilo of crap, you're going to spend a lot of time struggling to make that kilo somehow give you some result. And so always work on scales you're willing to chuck. You're willing to just toss if you have to when doing a reaction for the first time. I've got a bunch of maxims embedded throughout this talk that are memorable moments, and rule number one here is never change the reaction conditions substantially on an important scale up. So you're either fiddling with conditions or you're scaling up. Don't do both. You can do little adjustments around the edge as long as you recognize that, how little the adjustments are. You might say, look, I think I'd let it go a little longer, but since you're going to follow it by TLC, you're going to be watching that very, very closely. So it's not the riskiest move. But you never change big conditions. You never change solvents. You never change anything on a scallop and say, what could go wrong? And anytime you find yourself asking the question, what else could happen? The answer is all those things that you're too stupid to think about. So you want to minimize scale within reason. Why do I put within reason? There are reactions that are tough to run on small scale, and a combination of reagents being cheap and that particular challenge, sometimes it pays to amp it up a little bit. In this category, if it's a prep you're doing that requires a crystallization at the end or something, you might want to work with more. There are people who can crystallize a milligram. I don't happen to be one of them. Volatile compounds drive me bananas trying to make them behave themselves. And so if you have to make something that boils at 60 degrees, you got your hands full, you're going to want to work on bigger scale, unless you can separate it by a prep GC. I don't think we even have one in the building anywhere, so good luck with that. Again, emphasizing underneath rule 2 is microscale is much faster, much faster, and I'll show you why later, and I'll keep saying it till I get there. And the other thing about microscale is it allows you to work in the front of a synthesis longer. So if you're going through a multi-step synthesis, there are people who get great satisfaction out of bringing materials forward because A, the reactions already work, so it feels good. And B, you somehow think you need a big army at the front. The best synthetic chemists work at the front as long as they possibly can. If you're not working at the front of the synthesis, you are not making progress. You might as well sit in your driveway and rev your car and warm it up and think about your long journey and pretend like you are making progress when in fact you're not. So bringing materials forward is a necessary evil, but if you want to finish a molecule, you want to be banging. The more time you spend banging on the front of that synthesis, the more progress you're going to be making. And that's rule 3. I kind of jumped ahead of myself and I'm having problems with my cursor, my arrows. Okay, and that rule 3 is that emphasis. Okay, starting a reaction. The vessel. Oh, there are so many vessels now, and I'm just going to show you some. Everyone has their favorite vessel, whether they stole it from biochemistry or whatever. I'm just going to show you what I became acclimated to. You'll see all sorts of things. Whatever you do is what I'm about to tell you about how small scale accelerates your progress. Your vessel better be allow that to happen. If you're using a vessel that doesn't facilitate speed, then you're using the wrong vessel. So let me start with what's called a round bottom pipette. For years, my group wasn't using them at all. I finally got a student who was open-minded to get back to them. Round bottom pipette is shown in this picture here. This is 1/4-inch tubing. I have the glass blower make them. You don't buy them. This is 1/4-inch tubing. You can have different size bulbs on them. You have the glass blower make it because no one wants to have a reaction vessel break in the middle of a reaction. 1/4-inch tubing with a little polishing makes it perfect to put an NMR cap on the top. You can put septa. I really am an opponent of septa. Actually, an NMR cap with a needle poke through the top is better than a septum, in my opinion. Down here in the bottom is a stir flea. It's just a mini stir bar. I don't know where it gets the term flea from, but here's what's great about this, as opposed to a vial. This right here looks like about 500 microliters to me, if I remember correctly. The beauty of the round bottom pipettes is that the long stem allows you to clamp them and raise them and lower them into baths and stuff like that. And so as opposed to vials are hard to get a clamp onto. So that's why I lived and died by the round bottom pipettes. Okay, Kimball vials. Now, the awkward part of this is that I don't think these particular vials shown here, even though I give you the part number, I don't think they're available. Kimball Company at one point made them. We actually bought out the last of their supply. We actually have cases of them sitting in my laboratory. So when I retire, they're going to be left over, and someone will inherit them. But there's so many different vials out there, and Kimball I think does have vials that have NMR cap size openings, and this guy's a 5 mil vial. This guy's a 10 mil vial. I use these for the big scale reactions. This was a fairly large reaction for me. And again, Kimball vials, what I chose here, what really works well is that the NMR cap fits snugly in there. And so again, I prefer NMR caps over septa. Round bottom flasks. Y'all like round bottom flasks. I hated them. I don't think I used round bottom flasks more than 1% of the time when I was in grad school. Once you're in the round bottom flask, you're in a mess. You're in a very complex situation. I will use 3 Kimball vials rather than 1 round bottom flask. And so what do you put on as the top? Well, of a round bottom flask, I haven't shown a picture because y'all know what one looks like. You can have multi-neck. Avoid super complicated glassware setups. They're just more to clean, more to wrestle with. You can put a septum in the top. I don't like septa. They're gas permeable. How permeable are they? Well, if you take a volatile solvent like we took a vial once and put one of the pretty good grade septa, cap the vial with a volatile solvent that boiled around 45 degrees, and no hole in the septum, and watched the volatile solvent evaporate through the septum, and it was unbelievably fast. It was something like the vial's vertical, something like a 0.5 centimeter an hour it would drop, and so septa are air and moisture permeable. Instead, in a round bottom flask, I'd use a gas adapter, in particular the ones with the L-shaped thing. You just snap them and polish them, and then they have a straight access. You can shove a needle through them, and you can get access to the reaction through the gas adapter. Big fan of sealed tube reactions. It turns out these are 2 bombs here. They're called bombs for a reason, I think, because probably through the years someone has blown a few of them up. These are made they have Teflon joints here. They're a very thick wall glass tube. There's a penny, got to show a penny. They're very thick wall glass. Make sure your glass blower knows to make it out of very heavy grade glass. And that allows you to beat the snot balls out of a reaction by heating it way over the boiling point and so make sure you put it behind the shield. By the way, I'm going to add here that you can totally bury a lecture in safety stuff, right? Everyone's so paranoid their sphincter muscles are in a cramp. You be safe. I'm going to say you're in charge of watching all those other videos on safety. I'm not going to go through safety, but something like a bomb, it's patently obvious to put it behind a shield. It's also patently obvious to do stuff in hoods. There's stuff like that, but don't blame me if you're doing unsafe shit. This is not my job today to talk about that, except where I can see a serious problem. Sealed NMR tubes. And I think organic chemists probably are light on this one, and this is a phenomenal technique. The organometallic chemists love to do this all the time. And that is, if you want to watch a reaction go, or run a reaction even, or both, you put it in a sealed NMR tube. So we buy 9-inch NMR tubes, and then we get 3 clips out of it with the flame. And I tried to find a good video online for how to flame seal an NMR tube. It's completely trivial, but if you can find stuff that kind of looks like it, but I didn't bother to put it. In any event, you flame it up, you seal up your reaction contents in an NMR tube, and then you just watch it. And this is particularly important for stuff that can't be followed by TLC. So if you got something like you're trying to generate something that's going to hydrolyze on a TLC plate or be air sensitive, sealed NMR tube, don't underestimate the importance of it. And with polynuclear NMR spectroscopy, you can often do some really cool stuff. So if I were setting up multiple reactions in parallel, we're about to go on a campaign to look at a bunch of sodium HMDS chemistry, and everything's gonna be silicon NMR. Everything's gonna be silicon NMR, sealed NMR too. And then the capped Kimball vial. This is why I like the Kimball vials. Now you can't really see it here, but here's the 10 mil Kimball vial. There's a Sturfleet, one of the longer Sturfleets in the bottom. And there's a pinch clamp here, and what's critical, what you can't see, but right in there is a twisted heavy grade copper wire, which allows the bottom of the clamp to push against it. So it gives us something to grip onto. And on the top of the NMR cap is a penny, so that the top thing has something to bite onto. And so you tighten up the clamp, and I've heated THF for 24 hours at 90 degrees without any loss of THF underneath this pinched NMR clamp tube. Again, do it behind a shield or behind at least a hood sash, just to be safe. Okay. Rule number 4, scepter, moisture, and oxygen permeable and are consumed by many corrosive chemicals. My God, stop using scepter for long-term stuff. If you're going to stir it for more than an hour, put a gas adapter on. If you're going to store it in the freezer, never store anything under a septum in the freezer. That's just crazy. I once had a compound that was just a little bit hygroscopic, and in one flask hanging from my monkey bars, it had just a penny stopper. And another, it had a septum that was clean and new and no hole in it. And the septum, within a day, it oiled out, and the penny stopper went days and days without oiling out. A penny stopper, no grease, no nothing, is way, way better than a septum. So scepter are really short-term, minutes, hours, no more than that. And certainly don't shove anything in the fridge with just a septum. That's just stupid. Okay. Inert atmosphere, none, nitrogen, argon. Everyone has their preference. Don't forget that, if you're doing an LH reduction, you can go all batshit trying to get the flame seal in the flask and stuff like that, or you can add 10 mole percent excess. And so Louis Fieser once said, you should never add more than one equivalent of a reagent unless you have to. Well, Louis apparently never did kinetics, because bimolecular and trimolecular kinetics tells me that you always have to. And so you should always find a way to make the reaction robust. Pharma does it all the time. They test the robustness of the reaction by tipping it off, a specific set of conditions. And so, you can obsess all you want over nitrogen argon, but sometimes a little extra reagent solves that problem. And then the question is, do you need a dynamic or static? When you're running a reaction and that bubbler is bubbling away, blowing argon into the room, the only thing it's doing is trying to suffocate you. Sometimes just closing up the vessel is fine. And by the way, furious bubbling doesn't do any more than a trickle. And so I think about just shutting off the goddamn inert atmosphere, especially for stupid reactions, right? It's one thing if you're doing early metal hyper oxygen sensitive crap, but then you're not using that anyways. Closed or open system. Again, I'd close up the system. If it's really oxygen sensitive, be careful with things that involve hydrogen and stuff like that. But I'd go to sealed tubes. I'd go to bombs. I'd go to things like that. Now, here's one of the favorites. I love this. Here, notice there's a septum right here with a needle going through it, with a balloon hanging, and it's deflated. I hate balloons. Balloons are stupid. Now, balloons are more permeable than septa. So when you blow up a balloon, then with argon, you fill with argon, you're so impressed with yourself. You somehow think if you have a lot of argon pressure, it'll keep the oxygen out. Well, it turns out that the partial pressure of oxygen is independent of the partial pressure of the argon. And so the oxygen and the moisture are going to wander through that balloon. So this big inflated balloon is like a big oxygen and moisture collector. And again, you'll have a little trouble getting into your flask, but the balloon serves no purpose that I can tell. And if for example, you got a hole in your septum, then the balloon will blow the air out, and then it'll deflate. If you are worried about the expansion of of the gases above, and you want to have a pressure release mechanism, then in the very least deflate the balloon. Then it's not, at least it's not collecting oxygen moisture with a high surface area and a thin membrane. This is total placebo crap. An inflated balloon, I don't think does anything. Someone can challenge me on that, but I'll whip your ass. Sample reagent impurity. Oh, this is where it gets really interesting. This is where good synthetic chemists move like bat out of hell, and anal retentive slow-mos don't do well. So valuable substrates, I'll purify. You are 10 steps into a synthesis, taking some crude and pushing it through. Until you've at least optimized the prep, you know exactly what you're doing. But if you're working on the front of a synthesis, don't use crap. You know, the shit in, shit out model is absolutely true. So you purify your materials, you get them clean, because you don't need, it's hard enough to get a reaction to work without being garbage. Now, on the other hand, in inexpensive and easy prep, purify prior to use can be a colossal waste of time. I mean, how many of you guys have done something where you need to use some reagent like benzaldehyde, and then you set up some distillation apparatus with a Vigro column, and you have a cow and you collect 3 different samples, and then you use that to add a Grignard to it, right? That's just incredibly stupid. Just sometimes just use it. I mean, if it's got floating bugs in it and stuff, don't use it. There's all sorts of ways to quickly purify. Let's say you have something that's semi-volatile and you need to purify it, and you need to distill it. Then set up a short path, right? Here's a short path distillation head with a round bottom, and imagine there's a liquid in there, and you got, let's say it's benzaldehyde. So you run a little water through, you put a collecting flask, and you put the heat gun to it. You don't put it in an oil bath. You don't heat it up. You don't distill slowly. You put the heat gun. You blow the sucker over. I could distill it over in about 3 minutes. And that's good enough for so many things. Now, if at the end of the reaction it hasn't worked well, or you get some bio, and check by TLC if it's a mess. I don't know, but all those times that you do it just because you think real men don't use slightly sketchy materials, all that time you spend doing all that purification could have been used doing other stuff. And every once in a while, you get your butt handed to you. And every once in a while, you got to be more careful. But you'll find out soon enough. And if you're doing reactions fast enough, your failures are short-lived. Okay. So there's other things like filtering through a plug of alumina. This setup here will be shown over and over and over. This pipette with a little plug of glass wool down here that you can't see. Sometimes you put a little sand if you want, but you don't have to. And then solids. It could be silica gel, it could be alumina, it could be sodium sulfate. There's all sorts of cases where we need to filter something through a plug of something. In this case, I'm implying it's alumina. And you literally, let's say it's triethylamine and it's brown and it's ugly. You take a pipette load of triethylamine and you squirt it into the top of the pipette here, and then you put the bulb on, you squirt it through, and it'll come down out the bottom here, and it'll be colorless and clear and look really good, and it might be a placebo. The brown stuff might have been fine, but you feel a lot better. And the whole you throw this away, you take the flask, you use it. The whole process took 2 minutes, maybe. No more. Shouldn't take more than 2 minutes. Some people, their menial chores include setting up jarfuls, dry right jarfuls of pipettes that are pre-filled. You get bored, you fill a bunch of things with sodium sulfate, you fill a bunch of things with silica gel, whatever. They just grab one, then they become disposable. And again, here, synthetic intermediates, garbage in, garbage out. I always purify those. Maybe it's hypocrisy. I've never used these for solvent drying. We're moving on to solvent drying. I've never used the drying columns. They kind of came in, and we use so many different solvents that having drying columns for 5 somehow doesn't seem to help us. I'm going to leave it to you guys to figure out. I think this stuff comes through really dry, and so I think in a general synthetic laboratory you want to have one with hexanes and THF and blah blah, whatever your lab needs. So if you're starting up a lab, this is probably a good idea. But I don't need to tell some of you that because you're already in labs right now. If not that, then there's things like if you want to dry ethers, you use sodium benzophenone. There's other tricks. That's what we use. People occasionally use LAH, which is not great, and calcium hydride downright stinks. If you take calcium hydride and you can boil the crap out of a solvent with calcium hydride, that stuff you can make streets out of. You could use it as road building material. There's almost no reactivity to calcium hydride. You boil the crap out of it, you can then you can take that sample. I got tested for COVID yesterday. Interesting to see if my expiration date has come up or not. You can see, you can then take that calcium hydride dried solvent, add a sprinkle of LAH, and that fizzes. And if you take the LAH dried material and you add it to, you take that distilled material and you put it over sodium benzophenone, you can even see the evidence that that wasn't dry either. There are people who have studied drying of solvents for their thesis. I would shoot myself before I had to study solvent drying for my thesis. But they've studied it, and it turns out that even LAH leaves water in solution. And so what's the best drying agent? It turns out, and it's not the one we use in vast bulk, but it turns out dry molecular sieves. Now, how do you dry molecular sieves? You don't put them in the glassware oven. When you put sieves in the glassware oven, you're drying your glassware oven. You're not drying the sieves. What you do is you put them under vacuum at 160 degrees for 24 hours. So you put them on your line and you beat the tar out of them with an oil bath. And you can watch them jump around like jumping beans as they degas. And I'm told that if you want to know if sieves are dry, you put a little in your palm and sprinkle some water on, and if they're dry, they'll get hot. And so if you want to test sieves, just put them in your palm and sprinkle some water on. We also, to dry hydrocarbons, I've got written down here sodium benzophenone and tetraglime. This tetraglime trick right here was one that was which I picked out of a Bob Grubbs paper. We have subsequently discovered, and what it does is it takes a sort of a hydrocarbon sodium benzophenone still, which looks a little on the skanky side. It's not quite like THF where it becomes really homogeneous bright purple. It makes it look homogeneous bright purple. So it's like 10 mils of tetraglime for a liter. But doing some serious proton NMR work with that material, what we've discovered is that we get tetraglime fragments vacuum transferring over. So I'd be a little careful with that one. And then things like P2O5. It's been a long time since I used P2O5, but it's still on the list. Okay. Okay. Measuring samples and reagents. It turns out that if you measure solids, if you're going to do greater than 5 milligrams, do it right on the balance. And you don't do it on a top loader. Use a good analytical balance. If you don't have one, then get your boss to not be a cheapskate and get you a 4-digit balance. Less than 5 milligrams, or when high precision is needed, you make a stock solution. So if you make a stock solution in pentane or diethyl or something, measure out, how much. So say if a milligram of material, you had 100 microliters, take out 10 microliters, and then strip the rest back down to dryness. And even if it's not a valuable material, let's say you just need to add benzaldehyde, but you need to add a tiny quantity, then make a stock solution, use 10 milligrams of it, throw 90 milligrams away. It's not exactly ungreen chemistry. It's a lot better than being big scale. Liquids and solutions. Okay, here's one. This is a lost art. These are phenomenal. These are the microliter pipettes that biochemists use. And what they are is they're straight tubes. They're capillary tubes. They got a little mark right here. There's a little mark. They come in different sizes. They come from, I think it's 5 microliters, 10 microliters, 25, 100, and 150. Now, here's what's cool about them. You have this special adapter. It's like a tapered thing, so you can stick any of these different sizes up there. This is a tube connected to a syringe. Now, if this is wired to your monkey bars, this thing's hanging. It's just waiting for you to use it. And so it hangs down, and then if you need to measure something, you jam one of these microliter syringe pipettes in there, and you measure it. Now, I put it next to a 3x5 card because by chance, a 3x5 card has 10 increments, which I think they're ½ centimeter, if I remember correctly. 10 of them, and it happens to be right up to the line. and so that gives you actually measurable increments. And so rather than you, so I could easily measure 5 microliters with a 10 microliter pipette. And, and so these are great, and they're dirt cheap, and it beats microliter syringes, which that you bend the needle, and it costs about $150. And so this is, you guys really ought to. I used to suck up butyl lithium and shit using this. It's just not. They work really, really well. Someone ought to try this. If you do, send me an email. Say, hey Dave, that worked fine, or hey Dave, you're full of baloney. I hate the costly small microliter syringes. Grad students bend those needles faster than you can imagine, so I don't want to go near those if I can help it. Gas tight syringes, 100 microliters up to 20 mils. You get even bigger than 20 mils, I think. These are real horse syringes at that point. There are disposable syringes that you can get. I'm not a big fan of the disposable syringes. They all have their limitations. There's some that is like a one-piece plunger plastic that's crap. I mean, it's just barely usable. And then there's the ones with the rubber tip at the end of the plunger. And if you make the mistake of trying to use that twice, sometimes it swells a little. And then you got a syringe load of, you're pulling up a syringe load of something that may be valuable or, dangerous, like butyl lithium or something. And all of a sudden the plunger pulls out of the rubber tip, and you've got a syringe full of goo with the rubber portion and a plunger that's just got a knob on the end, and then you got to push the thing back down in and then try to pull it out, and you end up with a real mess. So I'm not a big fan of the disposable syringes, but there might be good ones out there that I'm not aware of. Dropping funnels. I'm not a fan of dropping funnels. I wouldn't use a dropping funnel unless it was huge scales. And here's the problem with the dropping funnel. So notice here it's got a round bottom flask. This is for adding a reagent slowly. So I got a pressure equalizing thing along the side, and you put your reagent in. So the first thing that happens is, as a rookie, you'll forget to close the stopcock. It's actually marginally not closed right there. It's kind of in the vertical position. And you'll pour your reagent right down in the flask instead of putting in the dropping funnel. So you say, okay, I won't do that again. So then what you do is you fill the thing up, and you want to add something drop-wise over an hour, 2 hours, or 5 hours or something like that. You might have inert atmosphere up here. Who knows? And what happens is you slowly try to tease that thing to give you the right dropping rate. And as you turn it and turn it and turn it, and then all of a sudden it just whooshes out on you and fills up the flask. And if it's an exotherm, you're picking shards of glass out of your face. So then the next time you tease it close to the point where it starts to drip, and then you start tapping the thing with your finger, smacking it with your finger, just little tiny taps trying to get it. And then you finally get it dropping at the right rate. And then you look up 2 minutes later, it's not dropping anymore. You could be adding diethyl friggin' ether, and that thing will stop dropping. So then you tap it again, then you whoosh it and you're flying again. These things suck. And so what I would do is instead I would use a syringe pump. Now here's a multi-syringe pump. You can't even see it. There's a small syringe right in there. They're programmable so that you set a plunger rate, you set a flow rate. It means that the next day when you go to do it again, the same reaction, you get exactly the same flow rate every time. You can load this thing up with syringes, big horse syringes, the 20 milliliters. So you get, this one I think holds 1, 2, 3. Looks like it holds 3. You could use that one plunger to add 60 mils of some material. If you're working over 60 mils, you're too big a scale, in my opinion. And if you're working over that, you can use a dropping funnel because wide open is slow even. So I'd use syringe pumps over a dropping funnel almost every time. Temperature control. There's all sorts of cool things. There's hot plates, of course, and there's baths you can put it in. There's thermally regulated cooling plates. I don't even know the physics behind how you cool it. I guess it's like a refrigerator, but I don't think it is. I don't think there's a gas expansion. But you could. Until we moved our lab and lost the thermocouple, we were using a cooling plate, and we could control the temperature. And it has feedback loops, right? It has a temperature probe that then allows the thing to turn on and off, and so you can set the temperature. I think you get on about -20 with those. You'll see one down below, a cold finger and cooling bath. Cold finger you stick in a bath, and a cooling bath is a big tub of liquid that's being cooled by a refrigeration unit. These guys tend to run pretty expensive, but in a kinetics lab like mine, that's the cost of doing business. You got a, room temperature bath. It's not a bad idea to put something in a room temperature bath because, maybe the room temperature fluctuates. I don't know, but an ice bath, right? You can make an ice bath. You can make a salt water bath if you want. You're getting a little anal retentive probably. That's a pretty subtle difference. Dry acetone, of course. I used to use carbon tet baths that are not good for your liver. But if you ever use one, you get some, I think it's the freezing point of carbon tet's minus 25. And what you do is you don't pulverize the ice because then you get this solid cake. You actually use chunks of ice, and then you get carbon tet cubes floating around, and that seems to work pretty well. There's a whole, if you go on the internet, right, that thing I told you to stay away from, well, now it's time to go to the internet. And you can look up various bath temperatures. I should have put a link, but I didn't. There's a whole bunch down to minus 116, and it's good to have one of those pasted up on the wall in your lab, so that if you ever need to control temperature, you can. There's another thing called drying pistols, where you can heat a flask by refluxing a solvent against the bottom of it. It's a very elaborate piece of glassware, but if you really need a certain reflux temperature, but why you wouldn't just set a bath, thermoregulated bath? I don't know. Okay, I'm going to call it right there because I don't know how long I've been going, but I sense it's been a while. And then I'm going to start up again. And our next topic will be monitoring the reaction. And I haven't yet shown you why microscale is the way to go, but we'll eventually get there, and we'll get to the punchline. And till later, adios.